Okay, hello everyone, and welcome to Spectral Geometry in the Clouds. So today it's a pleasure to listen to Theo McKenzie, who will tell us about the precise eigenvalue location for random regular graphs. Don't hesitate to ask questions, whether by unmuting yourself or in the chat. And Theo, the floor is yours.
Great. No, thanks so much for the invitation. It's really a pleasure to be back. And yeah, I just want to reiterate that definitely if you have any questions about anything that I say, don't hesitate to ask. I'd rather be more rigorous and more thorough, even if it means missing a couple of slides about how the proof works. So today I'll talk about how I can use some ideas in spectral geometry for a discrete problem, specifically one on graphs, and how this lets us solve an old problem in random matrix theory. So this is all going to be based on joint work with Jiaoyang Huang, who's a professor at the University of Pennsylvania, and Hongsor Yao, who's a professor at Harvard. Okay, so just in terms of like a rough roadmap, we'll talk about motivations, then some of the methods that we use in our proof, and then I want to spend some time talking about future directions as well. So starting with motivation. So I know that people are coming from different backgrounds here in terms of like discrete and continuous geometry problems. So I thought I'd give a couple of slides at least about the general motivation for these questions and specifically how that bleeds into problems on graphs. So specifically, we can think about the wave function. So this function, both of time and space, psi tx, which is governed by the Schrödinger equation, which relates the change in time versus the distribution in space. And the idea is that this function, given the parameters of the system, will tell us how a quantum particle will develop. And the idea is that if I look at this differential equation, this is a linear differential equation. So if I want to find how does this wave function develop over time, what I can do is just find its eigenfunctions and eigenvalues, right? So I'm interested in when I apply this differential operator, when I just get a multiple of the original function back, and then those will be my eigenfunctions, and then I can decompose my my wave function into these eigenfunctions. Okay, so here I've given the heat map of 3 eigenfunctions for hydrogen, and a generic question that we're interested in quantum physics is just for my system, what is the spectrum associated with it, and then what is the distribution of values in this eigenfunction? Okay, so I gave you the solution for hydrogen, but if I get a larger and larger atom, then this becomes a difficult question, right? At least in terms of exactly solving the system. However, Eugene Wigner observed that for many disordered systems, so like a heavy nucleus, the distribution of the gap between eigenvalues, so consecutive eigenvalues, seem to always follow this same distribution. And specifically, what he saw is that if you replace the Hamiltonian with a random matrix, then we get back the same distribution between consecutive eigenvalues. So this plot on the right is from one of Wigner's papers in the 50s. And what we have is a histogram of the gap between individual eigenvalues for uranium superimposed on what's expected for this random matrix, which is this curve here. And then the other curve, which goes down, is just like if the eigenvalues are independent, this is what it would look like. So the point is that rather than these eigenvalues occurring independently, they occur according to this large random matrix. Okay, so this gives this dichotomy, or this gives this rather this general theorem of theory of quantum chaos, where the idea is that if I'm in a system where my classical dynamics look chaotic, so the idea is that like if I can think about these billiard ball dynamics where I just bounce around, and if the movement as I do this is aperiodic and therefore ergodic, then this is like a classically chaotic system. And I can think about then looking at a Schrödinger equation on a system where the classical dynamics are chaotic. And the general observation seen by Wigner is that these spectral fluctuations will be like large random matrices. And there's actually a further observation too, that if I think about the distribution of these eigenfunctions, then they're approximately equidistributed. So this is a heat map on the right-hand side. And so what we can see is that it's generally well spread out, this eigenfunction. Okay, so this led physicists to suggest that there's a very strong relationship between these classical and these quantum dynamics, in the sense that if the classical dynamics are sufficiently chaotic, then the spectrum should look like that of a Gaussian matrix. However, counterexamples to this were given by Low and Sarnak, where they gave hyperbolic surfaces coming from number theory, which had strongly chaotic classical dynamics, but did not have this random matrix-like behavior. However, we can still think about this for a generic system, like, whatever generic means, right? So the first thing that I want to argue to you is that a nice way to think about a generic system is actually to discretize the system. So just think about the model on over some discrete family of parameters. And then the nice thing there is that I can just sample something uniformly at random. So there are other nice ways to think about something like a generic system. But yeah, for the purposes of this talk, we can just think about thinking about some discrete system where I can just sample something uniformly at random. So I'll go more into depth on what exactly I mean in a couple of slides. However, the nice thing about sampling this generic discrete system is that if I think about just a random graph, many families of random graphs have very rapidly mixing random walks. And we can think about this as some kind of analog to ergodic geodesic flow. So these like classically chaotic dynamics. And so what we can think about is specifically this Bohigas, Giannoni, and Schmidt conjecture in this context. And actually, this idea of quantum chaos in graphs is something that's been studied for a long time. So dating back to the work of at least the work of Koresh and Spolansky, and then also there's this fundamental result by Brooks and Lindenstrauss as well, where generically we're thinking about the Laplacian for a very large sparse graph. And rather than thinking about the behavior in the high energy limit, we think about behavior as the size of the system goes to infinity. So specifically as the number of vertices goes to infinity. And really, Schrodinger operators on these discrete systems has been considered for even longer than this, dating back at least to the work of Philip Anderson in the 50s. So what we want to do is think about a spectral geometry problem, and specifically a quantum chaotic problem on a graph. So first, I should at least talk about what the operator is that we want to find the spectrum of. And for the purposes of this talk, we can just think about the simplest thing, which is just the adjacency matrix. So we can also think about problems to do with the Laplacian, or there's also a natural idea Schrodinger operator as well for graphs. But for the purposes of this talk, let's just think about the adjacency operator. And the idea here is that if I have a graph, just like the left-hand side, there's a natural correspondence to a matrix where rows and columns correspond to vertices. I put a 1 in an entry if the two vertices are connected with an edge. I put a 0 if they're not connected by an edge. And the idea is that the spectrum of this adjacency matrix gives a large amount of information about the geometry of the graph. And actually, I think this is a nice symbiotic relationship, because if you have a problem in linear algebra, actually viewing it as a graph problem is often quite useful, because you can convert it into a problem about discrete spectral geometry. And having this viewpoint actually allows us to find very precise spectral information about the matrix. Okay, so what we'll think about is this adjacency operator. And specifically, we'll think about it in this family of random regular graphs. And this is some ubiquitous model if we want to create a sparse but very well-connected network. And this has been used in many different areas, statistical physics, computer science, theoretical statistics, others as well. And the way that we can think about this model is that I want to fix the number of vertices in my graph, and I'll also fix the degree of every vertex. So here I have a randomly selected 20 vertex 3 regular graph. So I have 20 vertices, and every vertex neighbors exactly 3 other vertices. And the idea is that if I fix n and d, then the number of these graphs is finite. So I can just sample one uniformly at random. And the idea will just be what is the behavior of eigenvalues over this family. And instead of thinking just about the adjacency matrix, it will actually be convenient to pass to this normalized version, which is just a divided by the square root of d minus 1. And this is really just convenient because it allows us to compare our operator to other families of operators. And one thing that I can say about this matrix is that, well, it's a real symmetric matrix, which is n by n, so it has n real eigenvalues. And these eigenvalues are going to be from d over square root d minus 1 to minus d over square root d minus 1. So the reason for that is that my largest eigenvalue is always going to correspond to this all ones vector, which is normalized here. Because the idea is that if I take this uniform vector and then I apply my adjacency operator, then every vertex will receive d copies of itself, and then I've normalized by dividing by square root d minus 1. So this will always be the largest eigenvalue by the Perrin-Frobenius theorem. And so all of my other eigenvalues will fall in this window. So a specific, if we're interested in the spectrum of this matrix, we can first of all just think about the second largest eigenvalue in terms of magnitude. Once again, this has a lot of applications, just in terms of the mixing time of the random walk, and generally encodes expansion. And so what we're going to think about is both the spectrum generically over this family, and then also the distribution of this spectral expansion as well. So let's first think about generic spectral behavior. So something that it's not too hard to show is that if I just look at my distribution of eigenvalues, as my matrix gets larger and larger, then this will converge to a specific spectral measure, which is the one that's associated with the infinite regular tree. And the idea here is that if I look at most vertices in my random graph, then locally they will look like a tree. So I'll get this type of local weak convergence. And the spectrum of the tree is something that's been well studied, first calculated by Harry Keston in 1959. And it's given by this explicit spectral measure that I've written on the right-hand side here. And this is called the Keston-McKay measure. So in the middle of the slide here, I've superimposed 2 plots. So the blue line is the density that's predicted by the Keston-McKay measure. And then the red histogram is the distribution of eigenvalues for a very large random regular graph. And what we can see is that these 2 things are very, very close to each other. There are, however, a couple of other things that I want to note about this plot. So the first one is that this measure does not witness lambda 1. So what we said on the previous slide is that lambda 1 is always equal to d over square root d minus 1, whereas this measure is always supported from -2 to 2. However, for now, we're just worried about weak convergence, which means that I can ignore an individual eigenvalue. And if you look at the slide, maybe very hard, but you can see that there's a single eigenvalue on the right that's outside of the spectral measure. And that's this single trivial eigenvalue lambda 1. The second thing that I want to note is that as d goes to infinity, this converges to the semicircle law. So what I mean is that if I look at my formula on the right-hand side here, as d goes to infinity, this term in the middle converges uniformly to 1. And what I'm left with is a semicircle. And the semicircle law is the spectral measure that's associated with a Gaussian matrix. And what turns out to be the case is that there's a fundamental relationship between the Keston-McKay law and the semicircular law. And this is really key in order to get this optimal type of spectral rigidity that we'll show in this talk. Okay, so we want to move past weak convergence though, and I want to start thinking about convergence of individual eigenvalues. And what we'll show is that in fact, these are also just determined by this Keston-McKay law. So once again, let's just focus on the second largest eigenvalue in terms of magnitude. So for these, there's the Allen-Lopana bound, which says that if I look at any d-regular graph, then the second largest eigenvalue and the negative of the last eigenvalue are always at least 2 minus little o, so n of 1. So note that there's a nice correspondence between this and this Keston-McKay law, because what this is saying is that these edge eigenvalues can't lie too far inside of the spectrum. Okay, so what this means is that the smallest that these eigenvalues could potentially be is if this inequality exists in the other direction as well. So that led to this definition given in this paper by Lubatsky, Phillips, and Sarnak, where they said that a d-regular graph is Ramanujan if, in fact, all eigenvalues which are smaller than d over square root d minus 1, so this trivial lambda 1, are in fact smaller than 2. So I have this very large spectral gap. And there are really two types of these Ramanujan graphs based on this definition. So one is I can think about the non-bipartite version, where I have lambda 1 is equal to d over square root d minus 1, and all other eigenvalues lie in this interval minus 2 to 2. And there's also a bipartite version of a Ramanujan graph, where I have two trivial eigenvalues. So lambda 1 is equal to minus lambda n is equal to d over square root d minus 1, and everything else lies in this interval minus 2 to 2. Okay, so these are like the best possible spectral expanders because this gap is as big as possible. Okay, so actually constructing graphs that satisfy these Ramanujan bounds is quite difficult. So in this original paper by Lubatsky, Phillips, and Sarnak, and also the same year Margulis, we're able to do this using graphs that are generated using number theory called Cayley graphs. And specifically, these graphs, what they provide is infinite families of graphs for when d is equal to p plus 1, where p is a prime. So Morgenstern was able to generalize this Lubatsky, Phillips, and Sarnak construction to work for when d is equal to p to the k plus 1, where k is some power. And then Marcus Bielman and Srivastava, using non-number theoretic techniques, were able to show existence of these Ramanujan graphs in the bipartite version for any d and n. So in terms of this right-hand side, the existence problem is more or less completely solved because this gives existence for any degree that you want and also any number of vertices that you want as well. However, in terms of just even showing existence of these non-bipartite Ramanujan graphs, if I want to do that for d that don't follow a formula like this, that has remained open. And moreover, even if you wanted to find other examples of bipartite Ramanujan graphs, non-bipartite ones would also give further examples of these by taking what's known as the bipartite 2 cover. Okay, so these are these optimal spectral expanders. So what about a random graph? Is a random graph Ramanujan? And the answer is almost. So Nogo alone conjectured that with high probability, a random graph almost satisfies this Ramanujan bound in the sense that lambda 2 and minus lambda n are with high probability, and those 2 plus some factor that goes to 0 as n goes to infinity, as the number of vertices goes to infinity. So this was proven by Joel Friedman and given an alternate proof by Charles Bornov. And if you look at these papers and follow the proof, what they show quantitatively is that the second largest eigenvalue is at most 2 plus something like 1 over polylog n. So my collaborators, Jiayuan Huang and Horngser Yao, gave an alternate proof using Green's functions where they improved this to like a 1 over polynomial bound, like 2 plus O of n to the minus 1 over 100. And actually, they show something stronger, which is that every eigenvalue besides lambda 1, we always know where lambda 1 is, so we can just throw it out. Every other eigenvalue, lambda 2 through lambda n, is very close to where we would expect it to be. So where would we expect it to be? Sorry, something accidentally got deleted here, but we can go just back to this this plot here. So where we would expect it to be is just based on this Keston-McKay law. And specifically, I can think about the kth eigenvalue as corresponding to, I have 1 minus k over n of my spectrum to my left, and then I have k over n of my spectrum to my right. That's kind of what it means to be the kth eigenvalue out of n eigenvalues. So we just set this value gamma k to be where this spectral measure hits for the Keston-McKay law. And then what we say is that the actual location of our eigenvalue versus where we would expect it to be is something like O of n to the minus 1 over 100. Okay, so we have these improving bounds, but what do we actually think is the right limit? Like, how far are these edge eigenvalues actually from 2 and minus 2? Well, in 2006, Miller, Novikov, and Sabelli posted a paper concerning a number of computer tests, and what they observed is that if you look at the distribution of lambda 2 and minus lambda n, then these seem to be Tracy-Whittam, which is the same distribution as the top eigenvalue of a Gaussian matrix, specifically a GOE matrix. So a matrix with independent Gaussian entries, which is Hermitian. So specifically, this led them to make the following conjecture, which is that if we normalize this distribution, so I take lambda 2, I shift it by subtracting 2, and then I multiply by n to the 2/3, then up to some small further normalization, this distribution of the second largest eigenvalue will converge to the Tracy-Whittam law. So exactly what we get for a Gaussian matrix. So I want to note here that before our work, this was actually known if the degree was allowed to scale like a polynomial with n. However, in this work, we're specifically interested in if d is a fixed constant. Moreover, in terms of the Ramanujan problem, what this would mean is that, well, if I look at the probability that the Tracy-Whittam distribution is less than 0 and then square it, that's approximately 69%. So if this normalization constant here were 0, and also lambda 2 and lambda n were independent, then what that would mean is actually 69% of regular graphs are Ramanujan, actually non-bipartite Ramanujan. So this thing that has been very hard to show existence for actually is common in the sense that a majority of graphs have this property. So finally, the other thing that this conjecture implies is that the correct order of fluctuation of the second largest eigenvalue should be something like n to the minus 2/3 plus little o sub n of 1. So this is basically the correct size of the window that my second largest eigenvalue fluctuates in. Okay, so I just wanted to go back and take a big picture perspective on why is this problem hard? Like, why is it hard to find existence for arbitrary d and n? And at least intuitively to me, the problem is that we only have some fixed small number of ways to think about these large expander graphs. So first of all, if I wanted to think about my graph as having some inherent geometric structure, if that geometric structure is Euclidean, then that will never work because graphs that can be well embedded in Euclidean space are always poor expanders. So for these number theoretic techniques, as we've seen, these are successful, but these give strong constraints in terms of the degree and the number of vertices because if I want these to actually correspond to groups that I'm interested in. So this method of Marcus, Spielmann, Srivastava is is successful in finding bipartite Ramanujan graphs, but the reason why this doesn't generalize to the non-bipartite case is that this can really only control one eigenvalue at a time, rather than control both lambda 2 and minus lambda n. And finally, even if we think about random graphs, being Ramanujan is only a positive probability event. So I can't basically say with high probability, my graph satisfies this bound, which means that it's Ramanujan. In order to show this Ramanujan bound, I really need a really precise description of the distribution associated with the eigenvalue. Okay, so let me now state our results. So the first result is that we prove this optimal eigenvalue rigidity. So you can first just look at the consequence, right? So specifically, lambda 2 minus 2 is at most n to the minus 2/3 plus little o sub n of 1. So this is like this optimal rate of fluctuation for the second largest eigenvalue. And moreover, we show a similar type of bound for every eigenvalue. So once again, we can throw out lambda 1 because we always know what it is. It's always d over square d minus 1. So if I look at any other eigenvalue, lambda 2 through lambda n, then the difference between that and where we would expect it to be, based on the Keston-McKay law, is at most n to the minus 2/3 times this factor, which gets smaller the further I go in the spectrum. So for example, if I'm interested in lambda n over 2, then the fluctuation of this eigenvalue is something like n to the minus 1 plus little o of 1. So I just want to note that this is optimal. So this matches what was conjectured. And moreover, it matches the Gaussian orthogonal ensemble as well. So what we're trying to show convergence to, in terms of like this GOE, the GOE has these exact fluctuations in terms of these eigenvalues here. And just to compare it to other results, like I mentioned before, Jiaoyang and Hong-Sur showed the same result, but a bound of n to the minus 1 over 100. And pretty much contemporaneously, like less than a week after we posted this paper, there was this other very nice paper, which gives a short proof that gives that with high probability, lambda 2 and minus lambda n are at most 2 plus n to the minus 1 over 6. So this gives a non-optimal bound, but it's a very short, nice proof. And also it generalizes to other families of random graphs as well. So yeah. Okay, and then our other result is that we actually prove this Tracy-Whittem convergence. So specifically, we show that if I normalize by this factor, so d times d minus 1 over d minus 2 squared, then what I get converges to Tracy-Whittem. And in fact, this is true for lambda 2 and also minus lambda n, and these two eigenvalues are independent. So what this means is actually a majority of graphs are non-bipartite Ramanujan. So they satisfy both of these bounds. And this gives, I just want to note that these results are in line with this type of Bohugas-Giannoni-Schmidt conjecture, where I take some generic family of graphs, and they satisfy very Gaussian matrix-like spectral statistics. One other thing that I want to note here is that you might wonder, okay, where does this factor come from? D times d minus 1 over d minus 2 squared. And it's actually quite natural because this gives the ratio in density between the Keston-McKay law and the semicircular law. So if we're comparing the fluctuations of the two distributions, that associated with Keston-McKay and that associated with the semicircular law, then we just need to renormalize by how many eigenvalues are in that interval. And this is just saying that once I do this renormalization, then whatever I get converges to Tracy-Whittem. Okay, so these are my results. Maybe I'll just ask if there are any questions about anything that I said so far.
May I ask a question, please?
Of course.
What happens with other statistics?
Oh, yeah. I mean, there are, for example,
two-point correlation functions or the form factor of the spectrum.
Yeah.
Do they
Uh,
also go with the same kind of scaling?
okay, so how should I? So what I would say is that like, in terms of the most precise information about my spectrum, right? In terms of like the actual distribution, et cetera, right? Like this we can achieve at the edge of the spectrum. But so like, for example, like if I'm interested in the distribution of like, so for example, if I'm interested in the spectral distribution, or even like you said, this like 2-point correlation function, like if I do it at the edge of the spectrum, then I can also achieve precise statistics. However, like in terms of getting something stronger than just the spectral rigidity, that's still unknown if I'm interested in the bulk of the spectrum, right? So like basically like this work, and then I'll mention at the end there's been a follow-up work. Give basically anything that you want to know about the Green's function and the spectrum at the very edge of the spectrum is true in terms of this Gaussian behavior, but it's still open in the bulk. Like if I'm interested in, for example, lambda n over 2. Yeah. All right. Any other questions?
So what are the values of C1 and C2 expected? So you said that that they make sense to you, but did we already think that they were the right one?
So you're saying like, were these the same C1 and C2 that came from this previous work? Basically.
Yes, like is part of the result that these are the values, or were we kind of thinking that they would be?
Yeah, I think it wasn't explicitly stated like what these values should be. I think, part of it is that if I remove this factor, like if I just look at d times d minus 1 over d minus 2 squared, like to the 2/3, that's probably something that's hard to at least immediately bear out from computer tests. But I suppose like if you think about basically like if everything that you wanted to be true were true, then this is what you would expect, in the sense that this is really like what the order of fluctuation is just determined by how far lambda 2 and lambda 3 are away from each other, right? And basically like lambda 2 fluctuates in an interval which is proportional to its distance to lambda 3. And this is really reinforcing that. So I think like even if maybe this constant wasn't explicitly stated beforehand, like ipso facto, it is quite nice. Yeah.
Okay.
Yeah.
I can say something. I think it's fair to say that in this old numerics, C1 and C2 were not determined, but in any sense, in any accuracy. It's only once they understand everything that it comes out.
Yeah. And like I think also just once again, like trying to numerically find like even something like this, I think would be quite challenging. So yeah, I think even being able to show this like type of Tracy Woodham behavior is quite impressive, at least in my opinion. But yeah. Okay, so any other questions? Like I said, I'm happy. Please interject throughout if anything else comes up. Okay, so I'll spend some time just talking about the methods that we actually use here. So let me start talking about the Green's function and how we use it. So first of all, actually, let me just give like a generic overview of how we prove this. So there are a number of specific problems that we have to deal with in order to get these very tight bounds. So the first one is that we want very precise information about the eigenvalues and also their distribution. So the first thing that you might try is to think about the distribution of the trace. However, the point is that this won't be accurate enough. So the trace really gives you information about the top few eigenvalues most naturally. And even then you can't get this optimal sharpness. So what we'll do instead is think about traces of matrix inverses and basically given information about all of these matrix inverses together, get very sharp spectral information. the second thing that we need to think about is that what does it mean to sample a graph uniformly at random out of all graphs of a given size? And basically, typically in probability theory, what we want to do is we want to split our analysis into a bunch of independent parts. So what we need to do is think about what are the independent choices that I'm making when I sample a random regular graph. So this won't be independent choices of edges, which is what you would get for something like Erdős-Rényi. Instead, what we'll do is do the independent choices of switching edges. And then finally, we need to think about passing from a high probability bound to a constant probability bound. And the way that we'll actually do this, which is basically an optimal level of tightness, is to add a small Gaussian perturbation and check the change in dynamics as we add this perturbation. And so this is this idea of Dyson-Brownian motion. And so this is basically the final step that allows us to get this strong Ramanujan result. Okay, so let me start talking about the Green's function. So once again, we're going to pass from thinking about the trace to thinking about the Green's function. So this, for this, I'm going to take a complex number with positive imaginary part. And what I'll do is the Green's function will be defined as h minus z times the identity. And the point is that because h has real spectrum and z is a complex number, this is an invertible matrix. So I can think about the normalized trace of this matrix. So I'll just call that Mn of z. And if I just break this down in terms of individual eigenvalues, what I can see is that this is some kind of average over eigenvalues of lambda I minus z inverse. And what I can think about this as is some kind of discrete integral over my spectrum. And more generally, I can think about the Stieltjes transform, so this normalized trace, for even a continuous spectral density, where once again, I just take this integral of rho of x divided by x minus c. So what information does this Green's function give us? Well, if I look at the imaginary part of the Stieltjes transform, then what we can think about is that this is some approximator, some smooth approximator of the number of eigenvalues in a fixed interval. So specifically, if z is equal to e plus I eta, so e and eta are real, then what the imaginary part of the Green's function of the Stieltjes transform tells us is approximately how many eigenvalues are distanced at most eta from e. Specifically, it gives this smooth version, which I have here. But what we can see is that if lambda I minus e is smaller than eta, then the term in the summand will blow up. And if it's smaller than eta, or lambda I minus e is smaller than eta, then this term will blow up. And if it's larger than eta, then this term will be small. Another way we can think about this is that if I fix eta and then I vary e, then I'll get a smooth blow up every time I see an individual eigenvalue. So really what we're going to do is that we're going to show approximation of the Stieltjes transform of a random regular graph to that of the Kessel-McKay law. So if we do this for eta approximately 1, this gives the type of weak convergence of moments that we saw earlier. But what we're going to do is do this for eta greater than or equal to n to the minus 1, which gives strong convergence. And really by this, by this previous work of Erdős, Yau, and Yin, it's sufficient to show very tight convergence of the Green's function. So what we actually show is some more general results, but a more specific and simplified version is that I want to say that the Stieltjes transform of my matrix, of my random regular graph, and of the Kessel-McKay law are very, very close to each other at all when eta is at least n to the minus 1 plus epsilon. And this is in some sense optimal up to this multiplicative factor of n to the epsilon. Okay, so how should I think about my Green's function? Well, there are basically two interpretations that I like to think about. One is I can think about the Green's function as a walk generating function. So specifically, I can take g of z is equal to minus z times I plus h inverse. I can expand that into different powers of h. And what this means is that when I perform analysis of my Green's function, I can really consider the contribution of walks on different parts of the graph. And this is basically where we get to use our independence, which is the independent choices that we make in one part of the graph versus the other. So the other interpretation of the Green's function, though, is as a solution to the eigenvector equation. So we can think of gxy as the response at location y given a point charge at x. So this plot here is a heat map of the imaginary part of the Green's function on the two-dimensional lattice. So this red point in the middle is basically this x value, and then what we see is that we get this nice oscillatory behavior, but also some exponentially decaying behavior as well. And the way that we can use this quantifiably is that the Green's function satisfies this word identity, which is to say that if I sum over the squared entries across a row, then this is equal to the imaginary part of the diagonal entry divided by eta. And basically using this type of identity allows us to beat these purely combinatorial methods. Okay, so we want to converge to the Stieltjes transform or the Kessel-McKay law. And basically we want to figure out what's special about this Stieltjes transform, like what makes it unique. And the point is that it will satisfy a very nice equation associated with it. So by just looking at matrix inverses, so I can take the shear complement formula, which tells me how to look at a submatrix of an inverse. And I can really think about this as some kind of walk generating function approach, which is to say that in terms of the infinite tree, if I look at the diagonal entry of the Green's function in the infinite tree, these are just like walks that start and end at a vertex on that tree. And I can write that in terms of walks starting and ending at each of its neighbors after I delete the central vertex. And this explicitly is just given by the shear complement formula that I give above. So specifically, MKM can be written in terms of the Green's function at the root of each of these d-1 area trees. So if I do this process again, then I can write the Green's function at the root in terms of itself by once again deleting the vertex and then looking at the value below it. And this gives this nice self-consistent equation, which says that I can write the value at the root in terms of itself. And specifically, this is the self-consistent equation that's associated with the semicircular law. Okay, and so basically, there are two takeaways from this type of analysis. One is that if I'm interested in the Stieltjes transform of the Kessel-McKay law, it might be easier to first pass to that of the semicircular law. And second is that the semicircular law is defined by this self-consistent equation, which I give on the right-hand side. So how did we get the semicircular law? We deleted a vertex and then looked at the value at a neighbor. So I'm just going to do the same thing in the graph where I look at every directed edge, I delete one vertex of the directed edge, and I look at the Green's function in the new graph with that vertex deleted at the neighbor. And I'll just take the average over the entire graph. And in fact, to show that we have this convergence of the Stieltjes transform, it's actually sufficient to show that this new operator Q is approximately equal to the semicircular law. And the way that we actually do that is by showing that Q is approximately equal to 1 over minus Z minus Q, which is the same self-consistent equation, which is satisfied by the semicircular law. And really, this is what we spend the majority of the paper doing, which is showing that with high probability, and once again, for eta optimally small, Q minus Y of Q, where Y of Q is just defined to be this right-hand side here, is optimally small as well. Okay, so how do we actually do this? Well, let's thinking about the probability space associated with this model. So I want to take the expectation of Q minus Y of Q raised to some high power over all D regular graphs. So once again, this is a bit tricky because there are many such graphs and the entries are not independent. However, the independence that we have is that over random edge swaps. So specifically, if I take a graph, I highlight two edges, and then I swap their adjacency, then the point is that in the random regular graph distribution, these two graphs are equally likely to show up. So specifically, it's equally likely that I see two edges that look parallel like this versus crossed. So the way that I'm going to use that is by randomizing the neighborhood of a given vertex. So starting with a vertex O, I look at its neighborhood. Then I randomly sample edges arbitrarily in the graph. Then I'm going to change the neighborhood of O. So I'll take all these edges and then randomly swap them. And the point is that if the edges that I sampled at the beginning were just random edges at B alpha, C alpha, then the new neighborhood of O is given by these vertices C sub alpha. And what we'll do is that we'll take the expectation of Q minus Y of Q to the P by further taking the expectation over this choice of B alpha, C alpha. And the point is that, once again, over this distribution, these two graphs are equally likely to appear. And then to get this optimal rigidity, what we'll actually do is that we'll iterate this process. So I will randomly sample this neighborhood B alpha, C alpha, and then I'll further randomly sample the neighborhood of C alpha itself. And specifically, C alpha will be the new center vertex, and then I'll sample these new edges C alpha 2, B alpha 2. And the idea is to iterate this process where we just further randomly sample neighborhoods of more and more edges. And what we're able to show is that when we take these expectations, the error of our approximation decreases. So just to compare, something similar was done in this previous work of Huang and Yao, and they were able to take expectation over something like n to the log n many graphs, but through some sharper analysis, we're able to sample over n to the n many graphs and do this type of iteration. Okay, so finally, I'll talk about these Dyson-Schwinger equations. So if I want to show universality of the actual distribution, then something I can do is use what's known as Dyson-Brownian motion. So the idea is that I start with my adjacency operator, and then I add a small amount of Gaussian noise. So specifically what I'm doing is I'm doing this matrix-valued Ornstein-Uhlenbeck process, and then the distribution at time t is going to be like, if I start with my original operator, I give it a weight that's going from 1 to 0, and then I'm replacing that with a Gaussian matrix. So basically, over time, I'm replacing my original operator with a Gaussian matrix. And what we'll do is we'll show that analyzing the change in the spectral statistics as I do this operation is sufficient to show universality of the distribution. So specifically what we show is that at time 0, so just the original matrix, has optimal eigenvalue rigidity. So this is like this theorem 1 that I showed you before. The second statement is that if I do this operation for long enough, so at t is equal to n to the minus 1/3 plus epsilon, then I end up with Tracy-Whittem statistics. So that just follows from previous work of Landon and Yao. And then the last thing that I want to say is that adding this Gaussian perturbation hasn't changed my spectral distribution that much. And so that's this third step, which says that for every time in this interval, the distribution of my second largest eigenvalue has not changed. And so the way that we do that is that we show this even tighter bound on the Stieltjes transform. Specifically, if I compare the matrix at time 0 and then at time t for t in this interval, then it satisfies an even sharper bound. Okay, so how would I do this? Well, the point is that I can't compare just to the semicircular self-consistent equation anymore, because I can't possibly approximate it with error less than 1/n eta, because I'm comparing a continuous distribution to a discrete distribution. So I'll never have good approximation at intervals of length smaller than 1/n. So really what I need to do is compare this discrete distribution of my random regular graph to the discrete GOE, so this discrete Gaussian matrix. And for that, I need an equation which is specifically associated with the Gaussian matrix and not with the infinite limit, not with the semicircular law. And that's given by these Dyson-Schwinger equations. And these are equations which can be derived by this Gaussian integration by parts formula. So one way to define a Gaussian is that it satisfies this equality for every polynomial f. So Dyson-Schwinger equations, they look like this self-consistent equation for the semicircular law. However, they have this small correction term that's associated with the finiteness of the matrix. And really what we do is that we show that our function Q satisfies these same equations up to some small error. So once again, up to some renormalization, which has to do with the change in the density of the two distributions. If I look at this equation Q minus y of Q, it's very close to satisfying the same Dyson-Schwinger equation, which defines the GOE. Okay, so how do I actually do this? I'll just say briefly, the idea once again has to do with comparing these random walks. So the idea is that if I look at my actual matrix, so Q is a sum over terms that look like this, something like GJJ minus remove I. So I can basically decompose that into different types of walks in my graph using this walk generating function interpretation. And I can similarly think about y of Q as a walk on a very simple graph, which is just the vertex J with two loops attached to it. And the idea is that I just want to compare the contribution of different types of walks in these two models. Okay, and generically speaking, we can basically just split on the type of walk that we actually use. So for example, if I'm interested in walks that starting at the vertex J, I can go out through one vertex, I can walk around and then go back through the same vertex. So that's basically this first difference that I'm comparing. And I can compare, let's say, different terms as well. Like I can go out through one vertex, walk around, come through the other vertex. So that's the second term here. And then I have higher order terms as well. And the generic idea is that under the resampling, ideally, if I just properly resample this Green's function entry, it should be like just taking the average over the entire graph, which would mean I get exact cancellation of with Q. And similarly, the second entry, so exiting through one vertex, coming back through another, should be like just randomly sampling an entry of my Green's function in my overall matrix. And that should, on average, be approximately 0. So these are just general heuristics. And really a large part of the proof is giving calculations to show that these heuristics are true. Okay, and I'll just say something, I'll just basically say like something very brief about this slide, which is like one way to actually do this is by using the Woodbury formula. So just thinking about the switch in my graph as some kind of low rank perturbation. So the Woodbury formula then gives the change in an inverse after I do a low rank perturbation. And this is the type of thing that I can expand around what I would expect from the tree. And this unfortunately doesn't have the same nice type of walk generating function interpretation, but it does give a very accurate bound. Okay, so let me just end by saying some future directions that I'd be interested in. So the first one, like was mentioned before from Uzi's question, is what happens with bulk eigenvectors and eigenvalues? So there's this recent work by He, Huang, and Yao that apply the result that I told you about to give edge eigenvector statistics. However, the bulk is still open, basically because we need this tighter level of precision because the size of the fluctuation of the eigenvalue is smaller. And a nice preliminary question would be, is there no gaps delocalization? So this notion of L2 delocalization for random regular graphs. So Rudolphin and Vershinin showed this for dense random matrices. It would be nice to show this for random regular graphs. Okay, so another question would be to use this for more general polynomials. So like I mentioned, this work of Chen, Garza Vargas, Trop, and Van Handel are able to think about more general types of families of matrices. So it'd be interesting to try to do Green's function analysis here. For example, I think a pretty straightforward generalization of our results would be to say that 83% of bipartite random graphs are Ramanujan. And I think basically if you follow this just the same proof through, you should be able to get that. Doing a more complicated model, I think we'll need some new techniques. But this would definitely be interesting to think about the distribution here. Okay, a third question, which I'd be interested in, and I'd be curious to hear what you all have to say about this is, could this type of technique of thinking about random resampling of the Green's function be used for hyperbolic surfaces? So to me, this is a bit tantalizing because there have been a lot of nice interplay recently between work to do with random graphs and that to do with random hyperbolic surfaces as well. So it would be interesting to see at least what is the distribution of the Green's function as I think about various families of these hyperbolic surfaces. And I want to say that these types of Green's function techniques do seem somewhat flexible in the sense that, for example, we can generalize them to deal with infinite graphs. So they're very nice when you're thinking about some kind of infinite limit versus the original graph. And also, there is a notion of graph hyperbolicity, and this seems to be quite key in terms of these chaotic types of spectral statistics for these random graph models. Okay, and then finally, I just want to say a more, let's say, computer science algorithmic type question, which is, can we show that every graph is close to a Ramanujan graph? So all of our analysis has to do with taking the expectation over all graphs. But it would be interesting to think about if I have a fixed graph and just take the expectation over edge swaps associated specifically with that graph, then can I show some kind of improvement on the distribution of the Green's function associated with that? And yeah, this, for example, a question here would be like, if I think about a Markov chain, which is generated just by switching random edges in my graph, how long does it take to mix? Like, can we use Green's function analysis there? Okay, so that's all I wanted to say. So we gave eigenvalue rigidity for all eigenvalues, Tracy-Whittem statistics for these edge eigenvalues, and then this implies that most irregular graphs are Ramanujan using the local Dyson-Schwinger equation and a recursive formula for the Green's function. So thanks so much for your time.
Thanks a lot, Theo, for today's talk. We have time for some questions now, so if anybody has some, please either ask them in chat or unmute yourself at the moment.
May I ask?
Yes, go on, Ozzy.
There is a very nice identity which is called the Bus-Bartholdi identity, which is particular for the irregular graphs and very helpful for discussing the spectrum or to derive trace formulae for them. I wonder if this was ever tried to approach the Tracy-Whittem side of the spectrum.
So is this related to the Ihara-Bass formula, or?
Which is, I can't hear you, sorry.
Sorry, can you hear me okay?
Speak slowly because I'm partially deaf.
Okay. Is this related to the Ihara-Bass formula that relates the non-backtracking walk and the adjacency?
It is touching there, but it is a algebraic identity, which
okay.
The advantage of it is that when you are using all kind of expansions, you don't have to use all the periodic orbits on the irregular graph, but only those which are not back reflected. So you don't go this way, you only go forward and then back. And that reduces the number of possible orbits immensely. And that is quite helpful. But somehow you describe very nice methods which have to do with periodic orbit expansion in some way. I mean, the Green's function can also be written in terms of periodic orbits, and actually you don't almost do it. So I just wonder whether such approach cannot be helped. Also there, for example, analytically, the Chebyshev polynomials have a very, very important role in this expansion. And there are many known identities and known behavior of such polynomials. They are classical polynomials. And these, we at least use them. I wonder if that can help you in your approaches and your questions.
Yeah, that's a good question. I think I probably know, something about this, but probably not as much as what you're saying. So definitely, yeah, if you want to talk more about it, that would be great. In terms of what I do know, like for example, Charles Bordunov, his proof of Friedman's theorem uses this non-backtracking matrix in the sense that he passes to just kind of like what you're saying, passing to thinking about the distribution of non-backtracking walks that of some very high power. And like you're saying, that allows him to reduce the number of terms that he has to consider and simplify the proof greatly. I also, so another thing that you mentioned is this relationship between Chebyshev polynomials and basically the infinite tree. And you're right, like the non-backtracking polynomials have this you can write them as this difference of two Chebyshev polynomials, which allows you to think about the spectrum in some very nice way. So yes, I think it is very enticing, and yeah, it would be nice if that gave that helped us get some sharper bounds for sure. Yeah.
I had a question, if I can ask.
Yeah, absolutely. Go on.
Yeah, thanks. Wonderful result. I'm interested in the power 2/3 and what you can do with moments and what you can do with Green's function. So if I understand correctly, Ramon and co have not got to the power 2/3 yet, plus epsilon. Is that correct?
That is correct, yeah.
So do you see, and of course you explained, I think, quite clearly, once you even at the power 2/3 to get the Tracy-Widom, what that further analysis that your Green's function is achieving. Do we understand whether the 2/3 at least, plus epsilon, the result that's maybe a year old by Yao and co, could that be achieved by moments? Is that something we understand or not?
Well,
I mean, why are they stuck? Why are they not getting the 2/3? The number 2/3 is the most important one, yeah, in the whole talk. Yeah.
Yeah, I think, okay. So from talking to them about it, and this is just something that they've told me, but it seems like actually so they have this n to the minus 1/6, and
Right.
it seems like the fundamental barrier to them is at n to the minus 1/2. So basically they can do this type of polynomial expansion and write so basically the way that this proof of n to the minus 1/6 works is that you write the expected trace as a rational function, right? And then you show that it's this rational function satisfies these nice properties that allows you to think about the limit as basically as the graph gets larger and larger in some fixed way. And so to them, basically using this technique, there's a fundamental barrier there at n to the minus 1/2. So I think if you wanted to go, okay, in terms of the way that I understand their proof, if you wanted to go beyond that, basically what they say is that you write this this Taylor expansion, right, of your expected trace, or more or less, or a Chebyshev polynomial thereof, and you say that, okay, if the function that I'm looking at isn't supported in this interval minus 2 squared d minus 1 to positive 2 squared d minus 1, then these first few terms behave very well. Basically, they vanish. So potentially would work, but you would just have to have very strong control over even more terms. And I don't know whether that's like how hard that would be for them.
Yeah, thanks. It's, I think, nice to understand sort of how fundamental the Green's function input is here, which from your point of view it is, and I think it is. Yeah.
Fair enough.
Anyway, I'm probably asking you about their work, which is probably, I should ask them. Thanks.
Thank you. Yes, go on, Zev.
This goes back to Uzi's question a little bit. How far away are you from controlling things in the bulk? So in the bulk, you have deviations from the Kessin-Mackay thing of size almost 1/n, a little bigger, just a little bigger. So that's sort of a rigidity. In random matrix theory, in the GOE, you expect something like a log n type thing. How far away do you think you are from that?
Yeah, that's a good question. I think there are definitely some new things that need to be done if we want to get the distribution in the bulk. And the main reason is that when we do this type of resampling, where we resample further and further neighborhoods, there's always some low probability event that the edges that we resample are, for example, are like right next to the neighborhood that we're already considering. And the point is that the probability of this is like n to the minus 1 plus epsilon, right? And that's fine when you're interested in the edge, because an error term like that is smaller than the order of fluctuation. But in the bulk, you need to be able to consider specifically what happens with these types of switches. So yeah, there is actually some barrier there. However, yeah, if we were able to do that type of analysis, then hopefully we could generalize our result to the bulk, because that would definitely be something that I'm interested in, is these bulk statistics as well. Yeah.
Okay, thank you.
Thank you for the question. Zev, we have other questions for Theo?
I mean, in that connection, how big a d do you have to choose as a function of n to get the thing in the bulk? Do you know? I mean, I'm sure you know.
Oh,
I mean, do you have to take d to be a small power of n, or so?
yeah.
Not really. Yeah. I mean, Yao has some results on that, I think.
Yeah, you mentioned it in one of your slides. I think
Yeah.
any small power.
Any small power.
Yeah.
Okay.
And I think if you like worked really hard, you could get like maybe like polylog or something like that. But it wouldn't extend to even for like a sufficiently large constant, it wouldn't extend.
Thank you. Are there any other questions for Theo? Well, I think we may have gone through those interrogations. Thank you again for this very beautiful talk, Theo. We'll reconvene next week for a talk by Jaume de Diospont on interior hotspots for convex sets. Thank you all for being there, and see you all next week.
Thank you very much, Theo.